In the last episode, we looked at a more intuitive definition of a limit and kind of used our intuition to determine what the limit would be as x approaches a specific value of a function by looking at the graph of that function. In this episode, we are going to be looking at a more precise definition of a limit. In this case specifically, the limit as x approaches infinity of f of x equals infinity. So in the last episode, we kind of saw that we had a graph where as x was getting larger and larger and larger, we saw that the value of f of x just kept increasing. But we're going to go over more of exactly what that means. Now, the first thing we have to do is we have to think about, well, what exactly does this infinity mean? Right? Because infinity isn't exactly a number, but is the idea of increasing and continually increasing to a very, very large positive number. So x approaching infinity, so the idea is x is increasing. X is always positive and increasing and going to very large values. And we see f of x, right? And we also see f of x is very large. So the first way to define this might seem to be, well, if x is large, f of x must also be large. And this is true to a point. But let's take an example of a function. F of x equals 1 million. Okay. If x is large, f of x equals 1 million. And 1 million is large. At least some might argue that. But does the limit as x approaches infinity of f of x equal infinity? Well, no, this is a constant, right? So x will be getting larger, and yes, f of x is large, but f of x remains constant, right? So we need a more precise definition than just x is large, f of x is large. Okay. Well, we noticed that in the last episode, our function was always increasing. So maybe x is large, f of x is large, and is also increasing. And this gets better. This gets us closer to our definition. But I'm going to give another example. What about 1 million x divided by x plus 1? And I might draw an example of this for those who haven't seen it. So this is another horizontal asymptote. And so if you were to graph this in a graphing calculator, you would see that even in a function like this, when x is large, f of x is large, and f of x is increasing. However, in this example, we still see that f of x is never larger than 1 million, at least when looking at very large positive values of x. So in this case, the limit as x approaches infinity of f of x, it is not infinity. It is still 1 million, a very large number, but this doesn't give us exactly what we want. Okay, so we make our definition better even so. X is large, f of x is large, f of x is increasing, and there also isn't this upper bound. It just keeps increasing. But there is a more specific way of kind of talking about that. And we'll go over that first with a graphical example and then with a more precise definition. So here we have a graph that exhibits this limit behavior, right? as x approaches infinity, so for increasing values of x, we see that this fits our example. So let's try to quantify that and make this precise. So for example, let's say we choose an x value. Let's call that x value a. And this a corresponds to a y value f of a. Okay. So now imagine all the x values greater than a. So we see in green, I've highlighted x being greater than a, right? So after a, we see that x is greater than a. Then what is f of x? Well, f of x, right, are these values up here. And we see that they're always going to be greater than f of a. Okay. What if we moved a around? Would this still be true? Would x being greater than a kind of imply that f of x is greater than f of a? Well, if we move a anywhere on the right side, then nothing would change, right? It would still be true. But let's say we move a over here. We can call this a sub 1 or something like that, where this, right, is the height of f of a sub 1. Okay. Well, if x is greater than a, right, which would now be in this area, well, we do have a value of x, right, which we will call x sub 1. And we see that with our f of x sub 1, that f of x sub 1 is less than f of a sub 1. However, this isn't the problem, right? Because we're only concerned with values of x that are large. So it doesn't matter that there is some a that's less. That doesn't satisfy that. All that matters is that there is an a, not every a necessarily, but that there is an a such that when x is larger than a, f of x is larger than b. All right, so basically what is this telling us? This is kind of a fancy way of saying that the function will keep increasing, starting at f of a, right? We start at f of a, and all values of a are going to be bigger. So therefore, right, if x is greater than a, f of x must be greater than f of a. So that's great. We include the increasing part. But there are still other parts that we need to take into account. So in the last example, we started with an x value, which we called a, and then went to a y value called f of a, and then we were to see, well, if x is greater than a, then f of x is greater than f of a. So now to get a different idea about this, we're going to do the reverse. So I've started with some b values, b1, b2, b3, b4. And we're going to see if there is some sort of a value such that when x is greater than a, f of x will be greater than this b. Suppose, right, b is b1. Is there some sort of x coordinate, some sort of a value, such that when x is greater than a, that f of x will be greater than b? And if we're just thinking about positive numbers, we see, well, yeah. For every single positive number for x, let's just say x greater than 0, we see, right, that if x is any of these coordinates, that f of x is always above b1, right? All right, now let's look at b2. So we want to see again, is there some x coordinate, right? Is there some a such that when x is larger than this a, will f of x be larger than b2? So first of all, because there are actually values of f of x that are less than b2, Let's just see where this is on the graph. Okay. So it's right there. So as long as x is in this range, then we see, right, that f of x will be up here, or here, or here, and so on. So there was a b, we found an a, and then when x was greater than this a, after this cutoff point, f of x was greater than this b. And we can do this again. We look at b3 and say, well, b3 goes to the x-axis about here. Our a is here. And so when x is greater than our a, right? So there's kind of this cutoff point. F of x will always be greater than b, right? Because it could be here, or here, or here, and so on. And we can do this again. We can do this with b4. So with b4 we say, and then we go down. All right, so all we have to do then is set our a here. So if x is greater than this a, then f of x will be greater than this b. And the idea is it doesn't matter how large we choose this b to be. Because this is approaching infinity, and when x approaches infinity, the limit as x approaches infinity of f of x equals infinity, we see that no matter how large we choose a b, we can still choose some x-coordinate, some sort of cutoff, some sort of a, that when x is greater than that a, f of x is greater than b. So here is the specific, the precise, the rigorous definition of this limit, the limit as x approaches infinity of f of x equals infinity. So once and for all, what does this mean? So we say, for all real numbers b, we can find a real number a such that when x is greater than a, f of x is greater than b. And I've kind of color-coded this so we can see all the different ideas. And using quantifiers, we can see here, for all b in R, so real numbers, there exists an a, also a real number, such that for all x greater than a, f of x is greater than b. And again, if you're watching this and you're seeing that, well, this is just a bunch of words, but how is this saying that the limit as x approaches infinity of f of x equals infinity? Well, again, we say we choose b to be anything, no matter how large, how small, any value in the x-axis. And we're saying that if this limit is what it says it is, we can always find an a value, some sort of x-coordinate a, such that when x is greater than a, so x is greater than this cutoff point, f of x will always be greater than b. So it's not saying that there is one specific place, but if some arbitrary b is given, then it is possible to find an a, no matter how large that b is, to see that after that cutoff point, that f of x will be in fact larger than b. And that is what it means for the limit as x approaches infinity of f of x to equal infinity.